In Friedel-Crafts alkylation reaction, benzene is a nucleophile and the alkyl halide is the electrophile. Since the nucleophilic character of the double bonds in benzene is much weaker than that of a single alkene, in order to lower the activation energy of this reaction, we need to enhance the electrophilic character of the alkyl halide. To do so, we add a catalyst in the form of aluminum chloride. The first step is preparation of the active electrophile. Aluminum chloride has an empty p orbital, and therefore it is a Lewis acid. Here's the empty p orbital. First step involves transfer of the 2 electrons from the carbon chloride bond into the empty p orbital on aluminum and forming a complex aluminum tetrachloride -1, which then behaves as a Lewis base. After chloride is expelled, what we have left is the carbocation, and this carbocation intermediate is our active electrophile that is subsequently attacked by the benzene ring. So the carbocation is much more potent electrophile than an alkyl halide. Therefore, we had successfully lowered the activation energy for the first step of the reaction. So now let's go ahead and show how one of the double bonds from benzene ring attacks the carbocation, which results in formation of the so-called valent intermediate. So here we have our benzene ring. We'll redraw the 2 double bonds that had not undergone any changes. And here let's put hydrogen and our T-butyl tertiary butyl alkyl chain, and carbon at the ortho position here is a carbocation. Let's take a look at what happened here. We had 1 hydrogen on each carbon of the benzene ring, since every carbon is sp2 hybridized. And now, since the double bond attacked the carbocation, we formed a sigma bond between the aromatic, what used to be aromatic carbon, and our alkyl halide. So we had a change in hybridization from sp2 to sp3. Effectively, this had destroyed the aromatic character of the benzene ring and caused a loss in stability. So what happens next, instead of substitution that we had observed in the case of alkenes, where the chloride, for example, would add to the carbocation, resulting in the addition product, instead, aluminum tetrachloride ion behaves as a base, abstracts the hydrogen, the 2 electrons from the carbon-hydrogen bond collapse toward where the new pi bond will be, which effectively restores the aromatic character of the ring. So we'll form a pi bond between the sp3 carbon, which will change back to sp2, and the sp2 carbon, which is the carbocation. The product, therefore, is T-butyl benzene with the 3 double bonds in place. Again, first step is in situ preparation of an electrophile. That electrophile comes from alkyl halide. The bond between the alkyl halide carbon and the chloride breaks heterolytically with 2 electrons going into the empty p orbital on the Lewis acid, aluminum. That results in formation of aluminum tetrachloride ion and the carbocation, which is a potent electrophile. Therefore, we had prepared our electrophile in situ, which is much more reactive than the neutral alkyl halide. And now benzene, one of the double bonds of benzene, attacks the carbocation. This attack results in formation of the sigma bond between the aromatic carbon, what used to be aromatic carbon, and the carbocation. This is the new sigma bond. We refer to this intermediate as Welland intermediate, named after Professor Welland from University of Chicago. And very quickly and readily, sigma bond between carbon and the hydrogen breaks, the 2 electrons collapse to where the double bond will be, restoring the aromatic character of the ring. Let's take a look at another variant of Friedel-Crafts reaction, acylation, where the electrophile is acyl chloride. Now this ring, benzene ring, is substituted. It already has the isopropyl group on. Isopropyl is an alkyl chain. If you look at the directing effects and reactivity table of various aromatic substituents, you'll see that alkyl groups direct subsequent group to ortho and para positions. Typically, when you have a small alkyl group, the major product will be ortho product, simply because there are 2 ortho positions. So statistically speaking, there is more chances for the electrophile to come near one of those ortho positions than only one para position. However, whenever we have a branched carbon at the benzylic carbon atom, tertiary or quaternary carbon atom, as sigma bond rotates freely at room temperature, any alkyl groups that are attached to the benzylic carbon will effectively block the ortho positions from further substitution owing to the steric hindrance. Therefore, the major product will be the ortho product. So again, the main thing to remember here that when you have a branched carbon atom at the benzylic position, whether tertiary or quaternary carbon, in this case tertiary, ortho substitution is difficult, and the major product will be the para product. Now let's take a look at the electrophile. Here we have acyl chloride consisting of 3 carbon atoms. We have carbonyl and the chloride. Aluminum chloride serves as a catalyst with its empty p orbital. First step will be preparation of the electrophile in situ. This bond will break heterolytically and 2 electrons will proceed to occupy the empty p orbital on aluminum, resulting in formation of aluminum tetrachloride ion, as we saw in a previous slide, and a carbocation that looks a bit differently. So we have carbons 3, 2, and 1. But this carbon remains sp hybridized. So we went from sp2 hybridization to sp. This is carbocation, acylium carbocation. So whenever you form carbocation, you go one level down in hybridization. For example, from sp3 to sp2. And here, since we started with sp2 and we removed one of the domains, the chloride ion, our hybridization at this carbonyl carbon is now sp, and therefore we have linear geometry, 180-degree angle. And this is our active electrophile. Benzene will now attack this carbocation from the para position. So we want to choose the double bond that is at the para carbon. Since we don't have the double bond drawn here in this resonance structure, we'll use this double bond. Double bond attacks the carbocation, giving us valent intermediate. So here we have hydrogen that was present to begin with. And we also have ketone, that's carbon number 1, 2, and 3. So ketone is at the benzylic position. Next door we have hydrogen with a full positive charge on the carbon. So again, our hybridization changed from sp2 on the benzene ring to sp3 on the valent intermediate. And now we need to restore the aromatic character of the ring. In other words, we want to make sure that we have 3 double bonds and every carbon is sp2 hybridized. To do so, we'll use aluminum chloride to deprotonate the carbon that had undergone substitution, and this bond will break, go toward where the new pi bond will be, and aromaticity of the ring is restored. So our product is paradise substituted benzene, the isopropyl and ketone.